From the first two lectures, we have learned the physical meaning of arbitrary coordinate transformations and a method to distinguish curved spacetimes from flat spacetimes. Now we are ready to discuss what is the physics behind curved spacetime. So, experimental observations, set of experimental observations, shows that spacetime is curved by anything that carries energy. Perhaps that was at the beginning was falling from aesthetic observations and based on a very few experimental facts. But now the number of experimental facts that prove this conclusion are enormous, and nobody among the scientists questions this fact. So, rephrasing the statement that spacetime is curved by anything that carries energy, we can say verbally that metric becomes a dynamical variable coupled to energy carried by matter. Our goal here to show that all we need to formulate general theory of relativity, equations of motion of general theory of relativity, is this guess that a metric is a dynamical variable coupled to energy momentum tensor, general covariance, and minimal action principle. We would like to find equations of motions for the metric tensor such that which relate on one side there is a geometry, on the other side there is energy. So we expect these equations of motion to be generally covariant. It means that the action from which these equations will follow will be invariant under general covariant transformations. So we have to build up invariant from the metric for the beginning. So from the metric tensor, we have at our disposal metric tensor, and we want to build up an invariance which will compose the action. Well, simplest invariant that one can, first of all, the action should be integral of a space-time of some density, and this integral should be invariant. So the simplest invariant that one can write in these circumstances is d for x square root of the modulus of g, where modulus of g, let me define the notations, modulus of g is a modulus of the determinant of the metric tensor, and d for x is just dx0, dx1, dx2, dx3. So this quantity, this integral, is invariant under general covariant transformations. This is just the volume of space-time. One can straightforwardly check that the square root, the transformation of the square root of the metric, well, that's easy to see. Like, if you make a general covariant transformation, this thing is transformed by a Jacobian of this transformation. And this thing transforms by an inverse of the Jacobian, and they compensate each other. As a result, this quantity is invariant. The problem with this quantity is that if one will vary it, one will apply minimal least action principle to this sort of action, to the action proportional to this quantity, one will obtain algebraic equation for the metric, because this quantity doesn't contain derivative of the metric. As a result, we don't expect to get anything but algebraic equations. Well, we will see that, in fact, a little bit later. But one would like to obtain differential equations, containing differentials of metric along space and time directions. And this equation will describe dynamics, how metric changes in space and time, while algebraic equations don't do that. Well, this is the simplest invariant. We need to go a bit further and invent some other thing, which contains derivatives of the metric and is invariant. That invariant we know from the end of the last lecture, and that is Ricci tensor, Ricci scalar. Well, there is a Ricci tensor, and we need Ricci scalar R, which is just g mu nu times r mu nu. So this is invariant. We have to integrate it over the volume to obtain the action. So the proposal for the action is as follows. S is equal to a integral d for x square root of g. Well, this is not the only thing. We have to add b integral of d for x square root of modulus of g times r. So these are two simplest invariants that one can write, and this invariant already contains derivatives, unlike this one. So these two together can give us something which describes dynamics. A and B are some constants which follow solely from experimental data and cannot be obtained on the symmetry observations that we have been applying so far. Well, this action describes only gravity. It doesn't describe any matter, anything that carries energy, etc., etc. Well, gravity can carry energy, but that's a separate story. So we have to add to this some matter action. Some action which contains matter fields or particles and describes interactions of them with the metric, with the gravity. Well, the simplest case that we have already encountered during the first lecture is action for the particles. So simplest example of this matter action is the following one, minus m integral over ds. And that is minus m integral over d tau square root of g mu nu of z dot mu, z dot nu. And that is exactly describes coupling of the particle to the metric. And that is an example of matter which we have in mind. But we will encounter by the end of this lecture a few more examples of this action. But at this point, all that we need to know is that this action is invariant under general covariant transformations, nothing else. For the derivation of Einstein-Hilbert equations, we will need that fact only. What remains to be done is to fix these quantities, and in total, the total action that we are going to work with is the following. It is 1 minus 1 over 16 pi kappa integral over d for x square root of modulus of g r plus lambda plus S matter, which contains energy metric tensor and matter fields or particles. So here kappa is the seminal Newton's constant, and lambda is so-called cosmological constant. We fixed these constants to agree with experimental observations. So about this quantity, everything is known. I hope to those who listen to these lectures, everything is known about this quantity. But what is lambda? Well, first of all, quantum field theory predicts this to be very big due to so-called zero-point fluctuations, while experimental observations in modern cosmology show that it is not zero, but very small. This point is the essence of so-called cosmological constant problem, but it has nothing to do with our course. All that we need to know at this point is just some kind of parameter, and we're going to consider this as an arbitrary parameter. So our goal is now to vary this action with respect to the metric.